We interrupt your regular scheduled program to bring you the latest of the bombing that occurred downtown, destroying half the city. This was a chemical bomb explosion, and many people are asking what causes such an explosion. So, to answer your questions of the explosion, we pass you over to Professor Singh, who could give us a better idea in the field of chemistry and what causes such chemical explosions. Thank you, sir. I am Professor Singh, and my specialty is chemistry. And to help you understand what happens here, there's certain objectives you need to know about the rate of a chemical reaction, right? So you need to know what is the rate of reactions. We need to know a little idea about the collision theory and also some factors that affect the rate of reactions to understand how this occurred. So I'll try my best to explain them for you.
Products. So what the reactants are is the substances that we are about to mix together, and the products is what we get from mixing these substances. So for instance, in the lovely image we see here, the reactants are the ingredients we are about to mix together, and the products is what we get from the mixture. So we get that. So as we mix these ingredients, we're able to get the cupcake, right? But during the reaction, the concentration of the reactants decrease as the concentration of the products increase. So what do you mean? Initially, before we mix the reactants, we will have no products and we only have reactants. Then as we start to mix the reactants, we realize we get some products. And then the more reactants we mix, the more products we will produce. So the products will be increasing, but simultaneously the reactants will be decreasing. So we're getting less of the reactants and more of the products. So therefore, if we can measure the decrease in the concentration of the reactants or the increase in the concentration of the product and know how long it takes for the decrease or increase to occur, we can then determine the rate of a reaction. So the formula we use for this is the rate of the reaction is equal to the decrease in the concentration of the reactant over the time taken for the decrease, or it could also be the increase in the concentration of the product over the time taken for the increase. Some reaction also produces precipitates, right? So a precipitate is where we have a solid is going to be formed in solution. So therefore we're going to have a visual effect of this, and we can use the fact of the precipitate being formed to determine the rate of reaction, where we can time the reaction. So in this experiment we're going to see now is where we have a common experiment we do in high school and school, that where we have sodium thiosulfate is going to react with some hydrochloric acid, right? So and we place a beaker, we just draw a paper X on a paper and place the beaker over the X, right? And the name of the experiment is the disappearing cross. So here we add our thiosulfate, right? And we can see, we're going to see by a little magic how this cross is going to disappear, right? So next, after we add the thiosulfate, we'll add the hydrochloric acid and then time the reaction, because of course we established that the timing is important, so we have a stopwatch right here. So we add the hydrochloric acid now, right? And we start the timer immediately, and then we'll mix it up to make sure that the chemicals are mixed properly for the reaction to occur, and then time it. So you're going to see the cross disappear. See, the cross is already disappearing, right? So it's not magic, it's just the precipitate is being formed and is now blocking our vision. State that particles first and foremost need to collide in order for reaction to occur. Then they must have sufficient energy, and they also must have correct. Right, so I know some of us may still not to understand what the collision theory is, so I'll give you a little analogy of it, right? So imagine you walk in a room filled with balloons, right? And someone give you a knife and say, hey, let's go pop in balloons, right? So if you take the knife and then point it at the balloon and say pop balloon, it will not pop, right? The knife must touch the balloon, right? So the same thing with particles. The particles must touch each other, right? So just as the knife must collide with the balloon in order for the balloon to burst, same thing with the particles. Particles must collide. Right, so that was the first factor. The second factor is if I was to barely touch the balloons with the knife, chances are they may not burst, right? So I need to touch the balloon with enough energy to pop the balloon. So it's same thing with particles. So particles could touch each other and sometimes reaction may not occur. So it must have sufficient energy for the reaction to occur. So we saw the energy is the activation energy. So the activation is the amount of energy for the reaction to occur. Some reaction may require more than energy than others, but they must have sufficient energy for the reaction to occur. Right, so that's the second factor, factor. And the last factor, if I was to touch the balloons with the handle of the knife, right, so it will not burst because the balloon, in order for the balloon to burst, I must touch it with the point of the knife, right? So that's coming the orientation point of the reactants, right? So reactants must have correct orientation in order for the reaction to occur, right? So the same 3 points we just saw with collision theory, let's have an analogy with the balloons, right? So must collide. Firstly, must collide. Secondly, they must have enough energy, and thirdly, they must have correct orientation. There's the concentration. So the general rule is that the higher the concentration of a reactant, the higher the rate of the reaction. Right? So if the concentration of the reactant is increased, it means that there are more reactant particles per unit volume. As a result, the particles collide more frequently, which increases the chances of effective collisions. Therefore, the rate of reaction increases, right? So we've mentioned earlier what is concentration. We mentioned again is the amount of particles we have in a particular volume. So if we say we have a high concentration, we have a lot of particles. We have a low concentration, we have a little amount of particles, right? And remember previously I told you when you're thinking about how factors are going to affect the rate, we need to think about how collision is being affected. So if I have a higher concentration, I have a lot of particles, so therefore chances of collisions will be higher, so therefore we'll have more collisions, and if we have more collisions, the rate of reaction will be faster, right? So that's why the higher concentration, the higher the rate of reaction will be. So now we have a little experiment where we're going to show the effect of the concentration on the rate of a reaction. So here we have a potassium permanganate solution, we have a hydrogen peroxide solution. So you're going to add a little bit of the permanganate to the test tube, and then we add a little bit of the liquid soap to the test tube. And after, we're going to add some of the hydrogen peroxide. So this is the strength of the hydrogen peroxide we have. So we're going to see how the reaction is going to occur and how quickly. So you're looking at the time as well. So as we mix the hydrogen peroxide, see that the reaction is very rapid, right? So it's the elephant toothpaste reaction, so we see how quickly the reaction occurs, right? So for next experiment, what you're going to do is doing the same thing with the permanganate solution. So we add the permanganate solution in the test tube, we add some liquid soap to the test tube, right? But what you're going to do a bit different this time is you're going to change the concentration of the hydrogen peroxide now. So we add in some water to the hydrogen peroxide to dilute the hydrogen peroxide. By adding the water, what we are decreasing the concentration of the peroxide, so the particles now are moving further away from each other. So by decreasing the concentration, we're going to see the effect that it may have on the rate of reaction. And so as we add it, we noting how fast the reaction will occur. Right, so the reaction still occurred, the same reaction, but it occurred at a little bit slower rate than the first reaction that we saw. Right, and the last reaction, what we're going to do at this time now, we're going to dilute the permanganate solution and the hydrogen peroxide solution. So we're decreasing the concentration of both reactants to show how the concentration is going to affect the rate of reaction. So now we're going to have less permanganate particles and less hydrogen peroxide particles, right? And we're going to see the rate of the reaction. So we start off the same procedure. We add some of the permanganate to the test tube, we add some liquid soap, and then we add even further diluted hydrogen peroxide solution and see what we observe. Right, so as we added, we realize the reaction is occurring, but very slowly. Right, hasn't come out, the test tube yet, but it's coming. But the concentration is the only thing that was different in this reaction, right? So the concentration is surely slowing down the rate of reaction. So then it proves what we done before: the higher the rate of concentration, the higher the rate of reaction. So here we look, right? So we just saw how decreasing the concentration will decrease the rate of reaction, right? So next question tells us to explain the effect on the rate of reaction if the concentration of reactant in a reaction is increased. So again, they want us to explain now, so it's a little more than just state as before. Explain what effect on the rate of reaction will have if the concentration reactants is increased. So increasing concentration reaction, what are we going to see on the rate of reaction? So pause the video now and think about the answer, write it down, and then we'll correct it. Right, so your answer should have looked something like this. If the concentration of the reactant is increased, this means that there is more reactant particles per unit volume. So as a result, the particles collide more frequently, which increases the chances of effective collision. Therefore, the rate of reaction increases.
Okay, you guys, hope you learned something about chemical reactions. And don't worry, not all reactions are this dangerous and explosive. There are reactions that do take a very long time. For example, rusting of a car is a chemical reaction that can take many years to go. So not all chemical reactions are fast. Thank you so much, Professor Singh, for enlightening us. I know I learned a lot, and I do hope those who are looking at this video learned as well. That's it for now. Take care.